Good afternoon, everyone, and welcome to the latest edition of the 2DCC webinar series. Today we have Dr. Shenxi Wang, who is an assistant professor at Penn State in electrical engineering and computer science. And today she's going to be talking mainly about optical spectra. So Dr. Wang, please go ahead.
All right, thank you, Kevin, for the introduction. I'm very glad to be here and share with you some of our recent works. The topic today I want to talk about is how we can measure and understand the optical spectra of layer material systems. So first, I want to give acknowledgement to my advisors, collaborators, and my students. So most of the works I will present today are in collaboration with these people. And of course, I want to acknowledge the funding source. And these works have been funded from DOE, NSF, and the 2DCC Center here at Penn State. So I want to introduce a little bit about my current group at Penn State. We call it SCOPE Lab. SCOPE stands for Sensing, Characterization, and OptoElectronics. So we mainly do three types of research in our groups. We do study the fundamental properties of some nanomaterials and some types of new materials. We also integrate these 2D materials with some plasmonic nanostructures in order to tune and manipulate their optoelectronic properties. And eventually, these integrated structures will go to the application in terms of sensing and photonics. So we are also recruiting new students and postdocs. So if you are interested, you're welcome to contact me and browse our group website. So this is a slide about 2D materials, but I think with this audience in 2DCC, I don't need to talk much about it. But I want to mention that 2D materials is a really fascinating opportunity for us to look at materials in another perspective. So in fact, if you look at this electromagnetic spectrum, you will find for every frequency range, you can find some 2D materials that can be applicable in this frequency range. So if, for example, if you look at the far infrared range, we have graphene, and that can be very useful in the far infrared applications because graphene has its plasmonic frequency in the terahertz range or far infrared range. At the other end of the electromagnetic spectrum, we have UV light, and in this range, hexagonal boron nitride or HBN can be very useful. It has a band gap around 6 eV, so that's applicable in the UV range. And in between graphene and hexagonal boron nitride, we have some materials called TMD materials. So this stands for transition metal dichalcogenide. So this is a group of materials of many group members. Some typical TMD materials have the band gap in the visible range, so they can be applicable in this range. Of course, we have another important electromagnetic range, which is the mid-infrared. And in this range, black phosphorus or some derivatives of black phosphorus can be useful for these applications. Except for these very common types of 2D materials, we have a huge library of layer materials for us to hunt for 2D materials. For example, we can have some elementary materials like silicene. We can also have some 3-5 materials like bismuth selenide and bismuth telluride. So these materials have traditionally been very interesting in the thermoelectric applications as well as for topological insulators, but they do have the layer structure. So the few atomic layer versions of these materials can be very interesting. We also have some other materials like tin selenide, indium selenide, or transition metal oxides. So, a very simple but important way to characterize these 2D materials is Raman spectroscopy. So this is actually an ancient technology about 90 years ago. So it was discovered by Sir C.V. Raman in India. Basically, it describes the inelastic scattering of the incoming photon onto a material. So if you look at this figure, you will find for elastic scattering, the outcoming photon has the same energy as the incoming photon, so there is no energy transferred to the material. But for inelastic scattering, the outcoming photon has a different energy than the incoming photon. So this energy is transferred to the material and causing the vibration of this material. So if we can plot the intensity of the scattered light as a function of the energy difference or the vibrational frequency, we can get a spectrum. So we call this a Raman spectrum. You can see from this Raman spectrum, there are several peaks, and each peak represents a vibrational motion of the material. So we know that the Raman spectrum is a fingerprint for the materials or molecules. Its measurement is also non-destructive. So in the modern way of measuring Raman spectra, we can shine laser onto a sample and analyze the scattered light to get a Raman spectrum. So in 2D materials, there are basically two types of Raman modes. The first type of Raman mode, we call it interlayer Raman mode or high-frequency Raman modes. So as the name suggests, you can see for these interlayer Raman modes, the vibration is within the plane. So actually, the vibrational restoring force is the valence bond between atoms. So these valence bonds can be quite strong, and therefore they can have high frequencies. So when we talk about high frequency in the Raman world, it basically means like over about 100 inverse centimeter. So here is an example of molybdenum-sulfide. In a high frequency range, we can typically see two Raman modes for molybdenum-sulfide, and their frequencies are around 400 inverse centimeters. So in a frequency much lower than that, we can see another type of Raman mode, which is called interlayer Raman modes, or low frequency Raman modes. So again, as the name suggests, this interlayer means the whole layer of the 2D material vibrates as a whole unit compared to the adjacent layers. So the vibrational restoring force is the van der Waals coupling between the layers. And you can also see we have typically two types of interlayer Raman modes. We have interlayer shear mode and interlayer breathing mode. So they have different vibrational directions. So as I mentioned, the vibrational restoring force for these interlayer Raman modes are the van der Waals coupling between the layers. So these low frequency interlayer modes can be very sensitive to the interlayer coupling. So that leads to the outline of my talk today. I first want to discuss how we can probe the interlayer coupling for the 2D materials. And then I'll talk something about the anisotropy as well as the application in sensing. So first, the interlayer coupling. So if we look at some 2D materials and measure their interlayer Raman modes, for example, this is a case of BP, we can see there are several low frequency or interlayer Raman modes for the BP samples here. But if we change the thickness of BP, we can actually observe different interlayer Raman modes. For example, if we just have one layer of BP, there is no interlayer coupling, so you don't see any interlayer Raman modes. But if you increase the number of layers to 2 layers, you start to observe some interlayer Raman modes. And as the number of layers increases, the number of low-frequency Raman modes and their frequencies and intensities all change with the thickness of BP. So these low-frequency Raman modes can kind of determine the thickness for black phosphorus, and it can be widely applicable to many other types of 2D materials. So in fact, in the field, people have measured the low-frequency Raman modes for many types of 2D materials. Here I list some examples of molybdenum-sulfide, graphene, molybdenum-telluride, and rhenium disulfide. So for all these examples, as you can see, if you change the thickness of these materials, the low-frequency Raman modes change dramatically. So we can explain this result using the linear chain model. So if you look at the left figure over here, I showed the vibrational modes of the interlayer shear mode. So if you look at 2 layers, there can be only one interlayer Raman mode or interlayer shear mode. And that is the top layer and the bottom layer vibrates in different directions. But if you have 3 layers, then you can have 2 modes. The top layer and bottom layer vibrate out of phase, but the middle layer is static, so it doesn't vibrate. Or you can have another mode, which is the top layer and bottom layer vibrates together, while the mid layer vibrates out of phase compared to the other two. And if you look at 4 layers, of course, you can have one more vibrational modes, which is so the top layer and the second layer vibrates together compared to the third and fourth layer, or you can have 2 other types of modes. So as you can see, if you have an increasing number of layers for these 2D materials, the number of low-frequency Raman modes you can observe can be increased. However, not all these modes can be observed in Raman, so that is determined by the specific symmetry of these materials and the specific symmetry for these vibrational modes. So here I list all the possibilities, but not all of them can be Raman active. So if you actually use the linear chain model, we can also calculate the frequency of these vibrational modes, which is actually the frequency you can measure in the Raman spectrum. So you can see this omega shows the frequency. It's related to the interlayer coupling, which is the K over here. So you can see if you're talking about breathing mode or interlayer shear mode, this K number value can be different. And this omega is also related to the number of layers, which is the M over here. And you can also see for a certain thickness of 2D materials, you can have different modes, which is determined by this alpha. So alpha can be an integer starting from 1 to n. So if you have, of course, a larger n, you can have more modes for this alpha. And in addition to those modes predicted using the linear chain model, people have also observed some other types of low-frequency Raman modes. So this is called the collective compression modes, or CCM. So this is CCM is actually describing the in-phase compression motion of all the layers. So this is basically because the interlayer coupling is strong enough, so it actually couples all the layers together. So for an example of BP here, you can see these C1H, C2H, C4H, or C4L are the common modes that we can predict using the linear chain model. But we can observe another type of mode called CCM, and this CCM cannot be fitted using the linear chain model. It can actually be fitted using this 1 over square root of n. So that is due to a different motion of these low-frequency Raman modes. What's interesting about these CCM is they can be very sensitive, and they are actually more sensitive to the other interlayer Raman modes to predict the thickness for up to about 40 layers. So if you look at the figure on the left over here, you can see, for example, if you look at the C1H mode, the frequency kind of almost has no change when the thickness is over 10 layers. But if you look at the CCM, its frequency still can be very distinguished to each other up to 37 layers, and also the intensity can be very strong. So we can also use the low-frequency Raman modes to study the substrate effect for 2D materials. So in this study, this is bismuth telluride on some substrate, and people have observed some low-frequency Raman modes, of course, for bismuth telluride, but they also observe an additional mode, which has the lower frequency than any of the other low-frequency Raman modes predicted using the linear chain model. So we call this IF mode. And this IF mode turns out to be the interaction between the layered material with the substrate. So this mode is actually sensitive to substrate. If you change the substrate, this mode will be changed. However, these IF modes are not currently successful to be observed in the 2D layers. And this is mainly due to the weak interaction between the 2D layers with the substrate. So you need to really have a strong interaction with the substrate for us to observe these substrate modes. So we have also recently extended this technology to study some other types of materials other than 2D materials. So in this example, we studied the superlattice. As you can see, our sample is gallium arsenide and aluminum arsenide superlattice. And we also doped the superlattice with erbium arsenide ion. So if we measure low-frequency Raman modes, we can see several modes around around 20 to 30 inverse centimeter. And these modes turns out to be sensitive to the doping level. For example, if you look at the 25% erbium arsenide doping, its low frequency Raman modes are dramatically different from the case for example, 8% erbium arsenide doping or references, which means no doping. And also, if you have different numbers of periods for these superlattices, you can also see different low frequency Raman modes. So you can see their intensities and frequencies are shifted compared to each other. So we know these low frequency Raman modes can reveal the doping level and number of periods. Compared to the high frequency Raman modes, they seem to be more sensitive to those factors. And what is also interesting is we know for superlattice, we can have an effect of brilliant zone folding. And you can see from this lower right figure, we show the calculation of the phonon dispersion relation for the superlattice. And we can actually, due to the brilliant zone folding, we can have the phonon modes frequency be folded over here. So we do observe these kind of 7 harmonics of these low frequency phonon modes. So if you look at these references, for example, the 300 period, you observe 2 modes around the 25 and 29, and kind of observe 2 other modes as their 7 harmonics. So that's actually due to the brilliant zone folding effect. So we talked a lot about what we can observe using this low frequency Raman spectrum. So how do we actually measure that? So first, let's take a look at the normal Raman spectrometer. So typically, if you want to measure Raman spectrometer, you have a laser shining onto the sample, and the scatter light needs to go through a filter, which filters out the strong relay line. So because most of the Raman modes have a frequency very close to the relay line, you need to filter out this relay line in order to observe these Raman modes. And then after the light is scattered, it can go through this diffraction grating, which separate the light according to their frequencies, and then we can see the spectra in the CCD. So to measure the low frequency Raman modes, you basically need to filter out this relay line very well. So there are basically two methods to do that. The first method is called a triple grating spectrometer. So you can see after the laser is shined onto the sample, we can send the light to 3 gratings. So as I mentioned, when the light goes through 1 grating, it separates the light according to their frequency. So if you actually filter out the center wavelength in this grating, you can filter out a little bit of relay line over here. But if you send the light 3 times to 3 gratings, you can actually filter out the relay line very well. So that enables you to see the low frequency modes in the Raman spectrum. So the advantages of these triple grating spectrometer is it is wavelength dependent typically. So you don't need to change those experimental setups if you want to use different excitation lasers for the Raman measurement. You can also observe both the Stokes and anti-Stokes modes simultaneously using these triple grating spectrometer. The disadvantage of this triple grating spectrometer is its collection efficiency is very low because light needs to go through 3 gratings, and there's lots of loss for the light intensity during the optical path. The second method to measure low frequency Raman modes is called a black grating filter. So this is actually a very good filter to filter out the relay line. So we can actually measure the low frequency Raman modes down to about 5 inverse centimeters using these black grating filters. And however, these black grating filters are wavelength dependent. So if you want to excite the sample with different wavelengths, you need to change a filter. So here at Penn State Material Characterization Lab, we have 2 very advanced Raman spectrometers with multiple lasers and with low frequency Raman measurement capabilities. And it's also equipped with TERS, the tip enhanced Raman scattering. So that enables you to see some very fine structures beyond the diffraction limit. So I want to go back in time a little bit and tell you that this low frequency Raman mode is actually not a recent invention. The first low frequency Raman measurement has actually been conducted in 1971 in the Xerox lab. So at that time, people were interested in this arsenide sulfide and arsenide selenide. So these are also layered materials. So you can see from these spectra, we can see several low frequency Raman modes for these two materials. So interestingly, the early terminology for these low frequency Raman measurements was actually called a rigid layer modes. So that vividly describes the very nature of these low frequency Raman modes. Because as I mentioned, if you measure the layer material, the whole layer vibrates as a whole unit compared to the other layers. So the layer itself is actually rigid. So back in the 1970s, many layer materials actually have been measured, including some that we are very interested in nowadays, like graphite, molybdenum-sulfide, gallium sulfide, and gallium selenide, and some others. However, nowadays we are more interested in dealing with the few atomic layer versions of these materials, because that enables us to do something else rather than the bulk material, which is we can stack different types of 2D materials together, because if you stack them together, you kind of create a new type of material which property is different from any of the other natural 2D materials. So here I show an illustration of the stacking of different 2D materials, and this stacking also enables us to study some very interesting physics or chemistry properties of the materials. For example, a very famous example recently is the twisted bilayer graphene. So it turns out if you can stack two layers of graphene with a twisting angle of 1.05 degrees, you can observe this model insulating and superconducting effect for this twisted bilayer graphene. And when you stack different 2D materials together, something important you want to pay attention is the interlayer coupling, because the interlayer coupling actually dramatically changes the property of this stack. So here I show an example of molybdenum-sulfide and tungsten disulfide stack. So as you can see, if we increase the time for annealing, which actually improves the interlayer coupling, you can see the photoluminescence emission of the stacked material can change dramatically. So practically, we want to find a method to conveniently and simply check the interface quality for the stacked 2D materials. And this can be essential for scientific discovery as well as device performance. So in our work, we tried to use this low frequency Raman mode, and we built a model system, which is a twisted bilayer molybdenum sulfide. So here, I first show a naturally stacked bilayer molybdenum sulfide. So this is called 2H stacking. You can see the bottom layer is the red triangle, and the top layer is the blue triangle. So you can see they have the rotational angle of 60 degrees. So now if I rotate the top layer away from the 60 degrees, I can get a random angle. So we call it theta. So this is a twisted bilayer molybdenum sulfide. In the experiment, we can build this twisted bilayer molybdenum sulfide using a transfer technique combining dry transfer and wet transfer. So this optical microscope image shows the result. So we can see the blue, this triangle of bottom layer, the triangle of top layer, and the bilayer region. So if I measure Raman spectra on the bilayer region, we can get both the high frequency range, including the E2G and A1G modes, as well as the low frequency range, including an interlayer shear mode around 22 inverse centimeter and an interlayer breathing mode around 35 inverse centimeter. So now if we look at the angle evolution of these low frequency Raman modes, we can see if you have different rotational angles, the change of the frequency for the interlayer shear mode can be more than 8 inverse centimeters. However, if you look at the high frequency modes, for example, A1G here, the change of the frequency is about 1.5 inverse centimeter. So the change of the frequency is actually due to the coupling strength between the two layers. So we know that these low frequency modes are several times more sensitive than the high frequency Raman modes, in detecting the coupling strength between the two layers. What you have probably also noticed is when the twisting angle is close to 60 degrees, you kind of see a big variation of the frequency for this interlayer shear mode. So this can actually be explained using the high symmetry patching and first principles calculations. So let's take a look. If you're talking about the bilayer molybdensulfide, there are basically 5 types of high symmetry stacking for the bilayer molybdensulfide. We have 3R AA stacking, and we have 2H AB prime and A prime B. So the first two have the rotational angle of 0 degree, and the latter 3 has the rotational angle of 60 degrees. So for these 5 high symmetry stackings, their interlayer coupling can be very different. So that results in very different low frequency Raman modes as calculated by DFT over here. So now if we take a look at a twisted bilayer case, for example, 56.5 degree, which is close to 60 degrees, we can see for this twisting configuration, we can find the high symmetry patches at this twisting configuration. For example, the black circle shows A prime B configuration, the blue circle shows AB prime, and the red circle shows the 2H. So you get a combination of different high symmetry patches in this twisting configuration. So now if we measure the low frequency Raman modes for this 56.5 twisted bilayer, we can see the bottom figure shows the experimental results. For 2H stacking, so for the twisted bilayer 2D material, compared to the 2H stacking, we have a little bit of red shifted interlayer breeding mode, but the intensity is a little bit stronger. So if you look at the calculated results, you will see the reason of this change is actually due to the introduction of AB prime and A prime B stacking. So the AB prime turns out to have red shifted interlayer breeding mode compared to 2H, and its intensity is also much stronger than the 2H stacking. So with the combination of A prime B and 2H, you get a little bit red shifted and a stronger interlayer breeding mode in the measurement. And the same goes for the interlayer shear mode. So if you look at the interlayer shear mode, the 2H gives you kind of a sharp interlayer shear mode, but for twisted case, the intensity is weaker. So that is actually due to the weaker interlayer shear mode in A prime B and A prime, together with 2H. So that is how we can observe these interlayer Raman modes for the twisted bilayer case. So now, if we have a twisting angle close to 60 degrees, but if we want to change it a little bit, the interlayer coupling strength, as well as the high symmetry patches, can change dramatically. So that actually dramatically changes the interlayer Raman modes you can observe. So that's why we can see a large variation of the interlayer Raman modes when the twisting angle is close to 60 degrees. And similar case goes for the case when the twisting angle is close to 0 degrees. You also get a combination of high symmetry patches when the twisting angle is close to 0 degrees. And therefore, if you change it a little bit, you can also see relatively large variation for these interlayer Raman modes. So now if we further rotate the top layer away from 60 degrees, let's say it's close to 30 degrees, and these high symmetry patches just become so small that they're almost not observable. So if you change the twisting angle a little bit, they're weakly coupled. So that actually gives you very a small variation for the interlayer Raman modes. Actually, when the twisting angle is close to 30 degrees, the interlayer coupling becomes so weak that you can almost see no interlayer shear mode. So some of our collaborators also did the same measurement on some other material system. So in this case, this is a twisted bilayer molybdenselenide. So similarly, you can observe some interlayer shear modes when the twisting angle is close to 60 or 0 degrees. And you can see a big variation of the interlayer breeding mode. But when you further twist the top and bottom layer away from 60 or 0 degrees, you can observe no interlayer shear mode, and the variation of the interlayer breeding mode also is very small. So in our measurement, we kind of predicted we can see these periodic patterns of high symmetry patches. So after a year, about a year after we published this work, some other researchers came out with the direct observation of these periodic patterns. So as you can see, this is a work of the stacked molybdenum with tungsten dicyanide. So they used STM as well as STEM to observe the stacking configuration. So you can actually see different stacking configurations using STEM. And also, if they use STM to scan the sample surface, they actually discover the sample surface is not flat. Actually, if the tip is on a region with AA stacking patches, this actually has a very large interlayer separation, and the interlayer coupling is very weak. So you kind of see a hill on the surface. But if you scan the tip onto some regions, for example, AB stacking, which has a relatively large interlayer coupling, the separation distance between the layers is smaller, so you kind of see a valley over here on the surface. So this twisted bilayer 2D material is actually quite interesting and attracted a number of research groups to study that. And in our work, we have studied this Raman scattering, but we also extend the characterization to photoluminescence. So it turns out in photoluminescence, in the bilayer region, you see a relatively weak photoluminescence intensity compared to the monolayer case. And this is actually due to the introduction of the second layer decreases the excitation emission yield from the direct band gap. So PR actually reveals some other information that we cannot observe in Raman. For example, the interlayer epsilon, the trion binding energy, and the excess doping effect from the substrate. So I'm not going to talk about these in detail, but you are welcome to refer to some typical references listed over here. So we also extended our work to some hetero layers rather than just twisted bilayer molybdenum. So recently we have studied this stack of HBN with tungsten disulfide. So we got this monolayer tungsten disulfide from Dr. John Redwing's group at 2DCC. So this very high quality MOCVD samples enables us to study the spectroscopic features of these stacked hetero layers. So as you can see, if we stack the materials together without annealing, we can already see some low frequency Raman modes around 25 inverse centimeters. But if we anneal that, which improves the interlayer coupling, we can observe another interlayer Raman mode. So it actually turns out if this LF1 label here is due to the coupling between HBN and tungsten disulfide. So this mode actually tells you something about the thickness of HBN. So if we change the thickness of HBN, we can see a frequency shift of this mode. So that concludes the part about the interlayer coupling. Next thing I want to discuss a little bit about is anisotropy of 2D materials. And we are interested in that because nowadays many new types of 2D materials have the in-plane anisotropy. So typical example is black phosphorus. So as you can see, the atomic structure of black phosphorus tells you there are two in-plane directions. It's a zigzag direction and armchair direction. So it turns out many of the material properties of black phosphorus can change dramatically along these two directions. And these properties include the mobility, the photoluminescence emission, the thermoelectricity, and the photodetectivity. So for example, for electron mobility in black phosphorus, the mobility along the armchair can be twice as much as the mobility along the zigzag direction. So we know that's important. It is important to conveniently probe the crystal orientation of the material. So how can we do that? Theoretically, we can also use Raman spectroscopy. So here I show a typical Raman spectra of black phosphorus. You can see in the high frequency range, we have AG1, AG2, and B2G modes. These are the typical high frequency modes for black phosphorus. So during the Raman measurement, if I change the polarization angle of the incident laser, I can get different intensities for these modes. So here I show an example of measurement. These polar plots show the intensity of these Raman modes as a function of the polarization angle. So you can see in this case, we have the maximum intensities for AG1 and AG2 corresponding to 120 degrees. And this 120 degree also corresponds to the minimum intensity of B2G modes. So we know this angle is kind of special. It can correspond to either the zigzag direction or the armchair direction. However, whether it is really corresponding to zigzag or armchair has caused a lot of debate in the field. There are some researchers believe that these maximums should correspond to armchair direction, and some other people believe that these maximums should correspond to zigzag direction. So we want to know who is correct, and we want to know why. So we did a systematic study, and here I show two examples of BP flakes. We first measure their crystal orientation using TEM diffraction pattern. So this is a precise and reliable way to tell the crystal orientation. So we can see for both flakes, the horizontal axis corresponds to zigzag, and the vertical axis corresponds to the armchair direction. So now, if we measure polarized Raman on both flakes, we can see for the flake on the left, the maximum intensities of AG1 and AG2 corresponds to 90 degrees or armchair direction. However, for the flake on the right, the maximum intensities of AG1 and AG2 correspond to 0 degree or zigzag direction. So it turns out the Raman anisotropy for different BP flakes can actually be different. So in fact, this is a little bit more intricate. So in this table, I show the measurement results of 13 BP flakes, and we also did the measurements using 3 excitation laser wavelengths. There are 532, 633, and 785. So there are several observations we can get from this table. So first, if you just look at one flake but excited with different excitation wavelengths, you can see their Raman anisotropies can be different, for example, for these 3 cases. And second, if you use the same excitation wavelength, but you are looking at flakes with different thicknesses, you can also see different anisotropies like these 2. And also, if you just look at one flake and the same excitation wavelength, but you're looking at AG1 and AG2 modes, their Raman anisotropy can still differ. So in fact, some other researchers also conducted similar measurements, but they used different excitation wavelengths. In this case, this is 441 and 514. So they can also observe the change of the polarization profile for Raman intensity. For example, in this case, we have a 5 nanometer thick BP flake, and you can see for these AG1 modes, the Raman profiles are the opposite for the 2 excitation wavelengths. So now we have a few questions. So the first one is, if we want to use Raman to determine the crystal orientation, it seems too complicated. So now we want to know, can we find another simpler method to determine the crystal orientation? Well, the answer is actually yes, and it's actually very simple. So we can use the anisotropic optical absorption in the visible range. So it turns out if you're looking at the optical absorption in the visible range, the maximum absorption is always along the armchair direction, and the minimum absorption is always along the zigzag direction. So here I show 2 BP flakes with 9 nanometer thick and over 200 nanometer thick. So you can see they have the same polarization profile for optical absorption, but their Raman anisotropies are the opposite. So this result has also been confirmed by some other researchers, both theoretically and experimentally. So you're welcome to refer to some other literatures in the field. So we know that this optical absorption anisotropy can be a straightforward way to tell the crystal orientation. And next, we want to understand why this is the case. Why is optical absorption simpler? So in order to answer that question, we want to refer to this selection rule of optical transition. So in the typical optical transition case, you have electrons in the valence band, and you have a photon entering the material. And this electron wants to absorb this photon and jumps up into an excited state. So in this process, two conservation rules have to be satisfied. There's energy conservation and there's symmetry conservation. So for example, if we are looking at this case, which is a trilayer BP, we can calculate the symmetry of the electron clouds at different energy bands. So here I show B3G, B2U, AU here are symmetry labels. So now, if an electron from this B3G state wants to absorb a photon and be excited to this B2U state, the photon energy has to be equal to 0.8 eV, so that's required by energy conservation. And the symmetry conservation requires that the symmetry of the photon or the polarization of the photon should not be along the zigzag direction. So in fact, if the polarization is along the armchair direction, the optical absorption reaches the maximum. So another case is this electron from this AU state absorbs the photon and jumps up into this B3G state. In this case, the photon energy has to be equal to 4.3 eV, and the polarization should not be along the armchair direction. So it turns out in our case, for BP and invisible range, we should always have this uppercase, which means the maximum absorption should be along the armchair direction. So you can also see this anisotropic optical absorption is due to the anisotropic electron-photon interaction. Now let's look at Raman. Why is Raman more complicated? Well, that's because Raman actually consists of three processes. There are two electron-photon interactions and one electron-photon interaction. So in a typical Raman process, you have electrons from the initial state absorb the photon and be excited to an excited state. We call it M state. So this is an electron-photon interaction. And then the electron from the M state scatters a photon and jumps into another state. This is called M prime state. So this is an electron-photon interaction. And in the final process of Raman, the electron from the M prime state emits a photon and relaxes back into the initial state. So this is another electron-photon interaction. So we can see the Raman anisotropy is actually the product of three anisotropies. There are two electron-photon interactions and one electron-photon interaction. So that makes Raman anisotropy more complicated than optical absorption, which only has one electron-photon interaction. And this method actually can be generalized to study many other types of 2D materials. So we tried this method onto some other materials, including gallium telluride and 1T prime molybdenum telluride. So for all these materials, they show the intricate Raman anisotropy cases, and these phenomena can all be explained using the optical transition selection rule. So this method can also be a useful way to study some other types of new 2D materials. So next, I want to discuss a little bit about the sensing application of 2D materials. So as we have seen, the Raman spectroscopy can be useful to study some of the material properties and to characterize the materials. However, for a long time, Raman suffers from its very low efficiency, which is lower than 10 to the minus 6. So that means if you have 1 million photons entering the material, only less than one of them will go through the Raman process. And this very low efficiency greatly limits the application of Raman in microanalysis. So about 2010, there's a new technology discovered, which is called Graphene Enhanced Raman Scattering, or GERS for short. So in this GERS, you can put some organic molecules you are analyzed onto the surface of graphene. So it turns out if you have graphene as the substrate, the Raman signals can be enhanced. So in this case, I show an example of PTCDA molecule. You can see when the molecule is sitting on graphene substrate, many of its Raman peaks are enhanced compared to the case without graphene. So this GERS technique actually can have several advantages. So for example, the signal can be very repeatable for molecules on graphene surface. It's also very uniform across the surface. The graphene surface is protective to the molecules. and there's almost no noise peaks because graphene is chemically inert. It's also atomically flat. And therefore, the sensing reliability for GERS can be very high. The cost of GERS is also very low because all you need is a sheet of carbon atoms. The enhancement factor for GERS, however, is not extremely high compared to some other technologies. But the typical enhancement factor can be about 10 to 100. So that can already be very useful for many applications. And what's also interesting is this GERS actually gives you the molecular selectivity, which means if you use different molecules to observe this GERS effect, their enhancement factors can be different. So this molecular selectivity can actually be quite useful in a number of applications. For example, in biosensing, say you want to detect a type of molecule in a drop of blood, but there are hundreds of types of molecules in the blood. How can you detect your target molecule? Well, if you have an enhancement substrate, and if this substrate is selected to your target molecule, your detection can be easy and precise. So for the same reason, this molecular selectivity can also be used in other applications like industrial processes, food monitoring, environmental safety. So in our work, we want to understand what is exactly this molecular selectivity. In another word, if you want to use this GERS to detect some molecules, how can you predict whether this molecule can have a strong GERS enhancement or not? So in order to answer that question, we made several hypotheses, and it turns out there are two important properties of molecules that can affect the GERS enhancement. The first one is the molecular homolume level. So these energy levels of molecules, together with the Fermi level of graphene, if these three levels can constitute a Raman resonant case, then you can observe a very strong Raman enhancement. So this part can be theoretically supported by the third-order perturbation rule of Raman scattering. Another important factor for the molecules is its structures. So if the molecular structure is the type that it can couple very well to the graphene surface, you typically can observe a strong Raman enhancement. So this part has been confirmed by the first principles calculations. So we also went on to study several more types of molecules and confirm these selection rules. In addition, we try to extend this technology. So it turns out this GERS effect actually works pretty well for some biomolecules. For example, I show a hemoglobin case. You can see when the molecule is on graphene substrate, many of its signature Raman peaks are strong enhanced compared to the case without graphene. And if we actually measure the relative variation for the Raman modes on graphene or on silicon, you can find when the molecules are sitting on graphene, its variation is much lower than the molecule on some common types of substrates like silicon. So if we want to use this GERS for biosensing, it has several advantages. For example, we can show a fingerprint of the molecules. It's very simple, non-destructive, and fast. Because it's also very low, we can also enable an enhanced reliability, which is key to some disease prediction. We actually have studied this effect for a broad range of applications, including blood cells, cancer cells, and neurotransmitters. One step further, we can also map some biotissues to study the spatial distribution of some biomolecules. So in this example, I show a brain mapping case. It turns out if we measure the Raman spectrum on a brain slice of a mouse, we can analyze the relative concentration of different biomolecules in the brain. And if we map out their relative concentration, we can study the spatial distribution of different biomolecules. And what's also interesting is we can also study the correlation between the spatial distribution for different biomolecules, which can be very useful for biomedical applications and studies. So besides Raman, photoluminescence, absorption, spectroscopies, we also extended a little bit to study some other materials, structures, and using some other techniques. about needs the so and then six example we 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 have used for the same use for the electron spectrum spectroscopy to start the defect. For to the materials we have also constructed some nano cavities to tune the optical properties for 2D materials And very recently, we have used some near-field scanning optical microscopy to understand the fine structures of some 2D materials. So in this case, you're looking at a nanowire of HBN, and from its Raman modes, we can see the fine structure way beyond the diffraction limit. So with that, I would like to conclude my talk. The take-home message would be the optical spectroscopy can be very powerful in probing many of the material properties, and it can be critical for scientific studies as well as device applications. And I show a little bit of sensing applications using 2D materials, and that means they show they hold great promise for some novel techniques in different applications. So that concludes my talk, and thank you for your attention, and I will open to questions.
So we have several related questions online, so hopefully we'll answer all of them. Basically, it starts with questions related to damaging TMDs or other materials that you talked about today during the Raman PL measurement. I think what they're referring to really is how are they damaged? And it seems like they're feeling like most of it is oxidation related. So TMDs especially. So can you talk about how you deal with that? How do you measure that? And then the follow-on is what is the statistical reliability of this data given degradation of materials?
Yeah, so typically for some TMD materials like molybdenum, they're not very easily degraded in air. So if during the Raman measurement, if you control the power level of the incident laser, you can kind of avoid this problem. But for some materials like black phosphorus, they are very sensitive to air, actually oxygen and water in the air. So in our measurement, we typically protect the sample surface using some polymers or some other types of coatings. So if you actually screen the materials from the air, and then you should be good.
So there's a different variety of sensitivity to air. So can you talk a little bit about your techniques? So you talk about shielding them from being exposed, but then you have things like gallium, telluride, black phosphorus, which are more sensitive. So do you have established protocols by material to reduce this oxidation potential?
Yeah, so for some very sensitive materials like black phosphorus, typically you want to, well, ideally, you want to do the exfoliation in some inert atmosphere, for example, in the glove box, and you just completely screen this material from air for the whole process. And then you want to coat it with some polymers or some protective layers for the Raman measurement. So yeah, so if you have black phosphorus, that can be very, very sensitive. But for some materials like gallium telluride, it's not that sensitive, but it's a little bit sensitive. So in that case, if you can protect the materials as quickly as possible after you make the materials, that can be good enough for you to study the Raman features. And in fact, for Raman measurement, some of the Raman measurements may not be that sensitive to a little bit of oxidation on the material surface. So for the case of BP, for example, have compared the Raman study with transport study. So it turns out transport is more sensitive to the oxidation of the material. So and Raman is not that sensitive.
So another question focused around the statistical reliability of, and they were focusing on GERS and how that affects the sensing applications. So talk about the reliability of the data and then how that's handled in understanding resolution and sensing. Yeah,
so typically for our measurement, GERS measurement, we typically do a number of measurements on one sample. So it turns out they can be very uniform. And also, if you do the measurement across time, you can see the signal is almost has no change. So it's also very repeatable.
So when you say over time, how long time? I think they're looking for some specific.
Well, in our case, we did it for hours, and that shouldn't be much change. For some other types of substrate, for example, the surface enhanced Raman scattering, varying. If you use some metal substrate, if you measure it across several hours, the signal degradation will be very obvious.
Okay. We have one follow-on, and then we could probably do some questions in the room. I think the clarification just came through that sample-to-sample variability is what some of these folks are concerned about. Not within sample, but sample to sample. So the reliability could repeat and so on and so forth.
Yeah, so you mean for the GERS measurement or?
For any of the techniques
Okay.
you talked about, but they were focusing on GERS here at the end.
Okay, so so the sample to sample variation basically determined by the quality of your sample. So in our measurement, we typically do mechanical exfoliation, mechanically exfoliated graphene flakes. The surface quality should be almost the same for one flake with each other. So the repeatability can be very good.
Any questions in the room?
Thank you. You showed the determination of the different biological components in one of the last slides. Is it done solely based on the hyperspectral image of the sample?
So the last slide is hyperspectral image.